Hello, everyone. Good afternoon. Welcome to today's wireless distinguished webinar. I guess this week this is our second one, so it's great to have two wireless webinars this week in 1 week. So for those of you who are joining us for the first time, please feel free to leave your questions in the Q&A section, and at the end of the talk, I will just read them to everyone, and our distinguished speaker could actually answer, and you can also have follow-up questions if you have enough time. Also, the webinar will be recorded, so in case you want to watch it again later, you have the chance to watch it on Rice EC YouTube channel as well. So with that, let me start introducing our distinguished speaker today. It's our greatest pleasure and honor to have Professor Urbashi Mitra from USC. Dr. Mitra, she is a Gordon S. Marshall Professor at USC with appointments at both EE and CS at USC. She received her bachelor's and master's from Berkeley and PhD from Princeton. She is a distinguished member of multiple IEEE societies, such as IEEE Information Theory and Signal Processing Societies. Also, the inaugural editor-in-chief of IEEE Transactions on Molecular, Biological, and Multiscale Communication. She has won many awards. The list is long. I'm just going to mention a few, which is the IEEE Women in Communication Engineering Technical Achievement Award, US Fulbright Scholar Award, and IEEE Communication Society Distinguished Lecturer. She is also the editor of multiple IEEE transactions, such as IEEE Transactions and Information Theory and Signal Processing. She's not new to Rice, for those of you who don't know. She was a TI visiting professor at Rice back in 2002. Professor Mitra, it's great to have you back, although we wish that we could actually have you in person, hopefully sometime in the future, when the situation gets better. So without further ado, Professor Mitra, the floor is yours.
Great, thank you so much. I just realized I had not turned off my email, so if the pinging gets too bad, I might stop in the middle, disable that, and come back. So it's unusual to be here with you this way. Rice is one of my favorite places. I've visited several times, including the wonderful sabbatical that Rahman mentioned. So I'm happy to be with you in what way that I can. I hope all of you that are in Houston survive the various storms well, and that your families are healthy and safe. What I want to talk to you about today is work that has been ongoing for several years in my group, largely architected by this amazing postdoc, Marcos Vasconcelos, and as time goes on, augmented by others. So there's also new work by Zhu Zhang, who was a visiting graduate student to USC from the Beijing Institute of Technology. And so let's begin. What I'm interested in largely are these so-called networked decision systems. And so for those of us who have been active in wireless communications, we often think of these networks as only having one role, which is to send signals back and forth and to communicate with each other. But a network decision system, which seems to be a more relevant model, if you will, for how communication networks and networks are evolving in the future, this encompasses a lot of different kinds of architectures, including networked control systems, wireless sensor networks. The models that we're going to present come up in economics. And if there is time, I'll tell you a little bit about some of the work that we've been doing on modeling bacterial populations, where we actually model each individual bacterium as an agent that has decision-making capability. Now, one of the things that challenges these network decision systems is the fact that the signaling that's going to occur happens over this shared communication resource, this communication network. And of course, there are many things that can create noise or imperfections in our communication network, such as noise, delay, quantization, dropping packets, limited connectivity, etc., we're going to focus in particular on a channel with interference. And my description or measure of interference is going to be quite specific. So I will get to that eventually. So here's the basic framework. And actually, you're going to see variations of this picture throughout the talk. So I want you to imagine that I have a collection of sensors, these UIs, and they are each individual decision makers. And I'll explain what their decision making means in this context. Each of them make observations, these XIs. And one of the decisions that they're going to have to make is whether they're going to communicate over this resource limited environment, which we are going to model as a collision channel. There's a very specific problem that I want to understand, which is if I have these N decision makers / sensors, and they have this shared network, is there a strategy by which at some destination, like a fusion center, I can estimate all of the observations of these N sensors, given the fact that this channel does not have unlimited resources or bandwidth? So essentially, the model for the collision channel is if more than 2 of these sensors communicate simultaneously, then I have a collision. And what I want to do is jointly design my communication strategy as well as my estimation strategy. What is the communication strategy? Well, that's the decision that each one of these sensors makes with respect to whether they should communicate or not. So there are lots of applications. I talked about a number of them in the beginning, but Internet of Things, cyberphysical systems, these are the network architectures that we predominantly see using or are having this kind of problem to contend with. And what you'd like to have in these systems is real-time wireless networking. If we look at the typical protocols by which we share communication resources, a lot of them require feedback and introduce delays. And so what we want to be able to do is explicitly deal with these collision events. And the nice idea here, which is becoming more common in, say, control systems, is recognizing that every action that occurs is informative. And so what we're going to see is that even collisions can be informative for us. So as my colleagues who know me well can tell you, I'm an optimist, which means I'm optimistically hoping that I can share a lot of information with you. There's a decent story that I want to tell. And so let's see how much of this tale I can get through. So I want to go through the problem formulation and specifically emphasize our notions of optimality. And I don't know how many control theorists are in the Zoom, but I can tell you as a more communication, signal processing, and information theory person, these notions of optimality are a little bit different from what I'm used to dealing with. And so this was a new learning opportunity for me. Talk about this collision channel, which we've already discussed, and the notion of implicit information, and then take the problem that I want to solve, step back a little bit, solve a simpler problem, and then recognize that it gives me a lot of information and intuition about the problem I want to solve. And there are a number of variations that we're going to look at in terms of these initial set of assumptions. And as I said, if there's time, I want to talk about some of our new work in modeling microbial communities. So as I said, my goal is to do this estimation over the collision channel. I want to introduce some notation. So I have these different sensors N, and they are going to engage in the following decision. Should I communicate or should I not communicate? So if my decision variable at sensor I is equal to 0, I stay silent. And if it's equal to 1, then I transmit. What I'm going to transmit is actually going to be 2 pieces of information. The index of myself, my identity, my sensor identity, as well as the observation that I make. I'm going to assume that all of my observations for the moment have some density that describes them. I'm going to assume that the observations are mutually independent of each other and that I have well-behaved density functions. So this communication policy that I have essentially boils down to determining the probability that I transmit given that I have a certain observation. And so that's what I'm going to call this UI of xi. And as I said, my goal at the destination is to actually estimate each one of those xi's, even though only one of them has the potential of being received by me at the fusion center. So this might seem like it's magic, But one of the things that we're going to use is the side information that I have, which is understanding in the end how my decision variables are going to be designed, as well as having some understanding of what those underlying probability density functions are. So if we were in person, I like to quiz people and give homework. So one of the quizzes I would have done is to ask, what is the optimal estimator that I want to use? And as we know from taking detection and estimation theory, that if I want to minimize my mean squared error, which is my objective function here that you see at the bottom of the slide, then I know that the right estimation strategy to use is the conditional mean estimator, which is shown here, right? Now, because of the fact that I'm communicating over this collision channel, computing this conditional mean estimator is actually non-trivial. So I said that we need to talk about optimality. So team optimality is the form of optimality that I believe all of us are familiar with. Given any decision strategy and any estimation strategy, the one that gives me the lowest mean squared error, that's my team optimal pair of decision strategy and estimation strategy. This implies what we call person by person optimality, which is weaker. And it's a little bit weird, but it clearly has a notion of optimality associated with it, which says, let's say I have this good estimation strategy, all right, then the person by person optimal decision strategy is the one that minimizes the mean squared error over all possible decision strategies. Alternatively, given a decision strategy, my person by person optimal estimation strategy is the one that minimizes over all possible estimation strategies. So especially with this complicated collision channel, which is simple in description, but introduces a lot of coupling, finding these team optimal solutions is very challenging. Finding person by person optimal solutions is easier, but not necessarily trivial. And we're going to see that that's true in this case. So we're going to really simplify things, although most of what I'm going to share with you extends and generalizes to more complex scenarios. So I'm only going to have 2 sensors, 2 observations, and a collision channel, right? And so now this is a reframing of what I've already stated in the context of a 2-sensor system. So it's going to seem obvious, but let's review what the collision channel does and the implications of choices. So let's assume in the first case, I have a single transmission, which is that I'm going to transmit from sensor 1. I'm not going to transmit from sensor 2. So S1 is 1, comma X1, S2 is null, and I receive perfectly at my fusion center the identity of the sensor that transmitted as well as its observation, right? If nobody decides to transmit, then I receive this null symbol. There actually isn't a collision, but I also have not sent any information. If both sensors decide to transmit, I have a collision, which has its own symbol, which means I can identify when a collision has occurred, which means I can tell the difference between a collision and no transmission. And what I want you to see through my slow walk through all of the different possibilities is that in this situation, given my received signal, I can always figure out what was U1 and what was U2, right? Like I know what decision was taken. If there's nothing, I know if it's the null symbol, I know nobody transmitted. If it's the collision, I know both of them transmitted. And if I receive something correctly, I also know that, the other sensor did not transmit. And so this—
Rahman, can we ask questions or not?
I'm okay with it.
Of course, yes. Go ahead.
Okay. The reason I'm interrupting is that I think this may be a clarifying question.
Please.
Now, you're saying that the decision UIs are taken at the sensor level independently?
Well, in this case, it will be so. We're going to actually, it turns out that a good decision strategy can be implemented independently at each one of the sensors.
Okay. And then the density, you said that the density of XIs are nice. And then the question then is, are they the same for all XIs or the densities are different for each XI?
Okay, so excellent question. We're going to treat the first case first, and then we're going to move to the second case in an intermediate fashion, but eventually get to the case where the densities are arbitrary.
Thank you.
Okay. So actually, just for the entire audience, I'm more than happy to take questions in the middle of the talk. I think it makes it easier for you to understand what's going on, so don't hesitate to do so. So a point that I want to make here, and I hope that you see that, is that the collision channel is actually fundamentally different from the packet drop channel. I actually have more information through knowing when I have a collision or not. Okay, and this is something that we're going to exploit. So this may seem incredibly simple, so let me try to sell you on why this is an interesting problem. This is what we call a team decision problem with non-classical information, in the sense that each one of the nodes in here has asymmetric information about the environment. And because of this collision channel, this mean squared error is actually non-convex, right? And so the overall problem is not a convex problem. I cannot apply my usual strategies or even numerical strategies in order to solve it. So I need to go a little bit deeper. Okay, so now I'm going to cheat. I very deliberately explained to you the problem that I wanted to solve, and now I'm going to step back and solve a different problem. So I'm going to make things seemingly very simple, but they're still going to be interesting. So before, I told you that each one of these sensors is going to make an individual decision as to whether they should transmit or not. What I want to do now is take that decision-making authority and combine it with my collision channel, which is to say, I'm going to now design a scheduler, which means I can ensure that there's never a collision because I'm going to tell each sensor what to do, okay? Clearly, if I can design an optimal strategy for this environment and analyze its resulting performance, in terms of mean squared error, I have a lower bound to the decentralized problem that I want to solve, okay? But, don't worry. In the words of, some action heroes of the past, we will be back. We will come back to this problem. But even this scheduling problem is very interesting. So now what do we have? And I'm going to seemingly also make things simple. So now I'm going to assume that my xi's are zero mean Gaussian. I have this scheduler. The scheduler is now going to output essentially two decisions, one or two, which corresponds to, does sensor 1 transmit or does sensor 2 transmit? And my remote estimator is going to receive one of these two observations, as well as the identity of the one that transmitted, which means it's going to know the identity of the sensor that did not transmit. Okay, so now I want to design this U, this scheduling policy, and this E, this estimation policy. Okay, as before, same mean squared error that I want to minimize over the choice of scheduler and estimator. So I'm going to tell you a potential solution, and then we're going to go and show that this solution is in fact person by person optimal, okay? And so the solution for the scheduling policy is that I look at my two sensor observations and I ask myself, which one is larger in magnitude, right? And the one that has the largest magnitude, that's the one that I'm going to transmit, okay? Now, in the case where both of my observations have the same probability density function, which in this case means the same variance, maybe this is not too surprising. But what is going to be surprising is that even in the case where we have different variances with zero mean and independence, this is still the right thing to do. And then I have what I'm going to call the mean estimation strategy. And how does that work? Well, for the signal that I receive it perfectly, right? So I don't have to work hard to estimate it. I already know what it is. And what I'm going to do for the observation that I do not receive, I'm simply going to replace it by its mean value, which in this case is 0. Okay.
Now,
Yes.
Ubli,
Yes.
I'm surprised because I would have guessed that you would send the one with the larger variance.
Ah, thank you. Checks in the mail. We will get back to that.
All right, thank you.
That is actually going to incur a larger overall mean squared error. And we will see this with great graphic impact.
Wow, nice.
Okay, maybe it's not that great, but it's visibly worse. But as I said, I appreciate that you say that because that would appear to be the right thing to do. But again, it's the scheduling and the nonlinearity, if you will, that's introduced there that tells us that this is not the right strategy. So if my two sources are independent, and again, remember, I'm assuming that they're zero mean, Gaussian, then this max scheduling mean estimation policy is in fact person by person optimal. And we're actually going to walk through the proof of that. As Benham very correctly assessed, the open loop scheduling strategy is to let the sensor with the largest variance communicate. Why am I calling this open loop? It's because that's what you would do if you did not know what the observation is. But I have the side information of knowing what X1, the realizations of X1 and X2 every time I want to transmit, okay? And so this observation-driven scheduling, this is the one we just discussed, which is to let the sensor with the largest measurement transmit. So remember how the person by person optimality statement goes. You fix either the scheduler or the estimator, and then you search for the best other thing, all right? So we know that the MMSC estimator, right, for a given scheduling policy should be this conditional mean estimator. If I receive sensor one signal, then I don't have to estimate X1, but I do need to figure out the conditional mean estimator for X2, and same in the other direction. So this is just, this is baby, what do you want to call it? Expectations, if you will. So if I suppose that my scheduler is this max scheduling scheme, all right, so now I'm fixing my scheduler, right? And I want to figure out what the best estimator is. You have this expectation or this set of integrations that you have to do, all right? And this actually translates to the following set of expressions. So what I want you to see in the numerator here is that I'm integrating from, you know, minus some number to some number, x2 times its density. X is an odd function. F of x in this case, because it's zero mean Gaussian, is even. And so that integration goes to 0, all right? And so this tells me that if I'm using this max scheduler, then my conditional mean estimator is my mean, which in this case is equal to 0. So on the flip side, if I fix my estimation policy, and for the moment, I'm just going to keep it arbitrary with these eta functions, and I go through and I write out the expression for my cost function, you can see that I'm going to essentially I have the sum of these two terms, but only one of them is going to be active depending on the schedule that I choose, right? And so if only one of them is going to contribute to this mean squared error, I want to keep the one that has the smallest contribution. And this boils down to the following scheduling policy, which says that I have this generalized nearest neighbor condition, which is x1 minus the estimate for x1 magnitude squared should be greater than x2 minus its estimate. Okay, and that's when I choose sensor 1 to transmit its information. And if I'm in the situation where I have this conditional mean estimator, which in this case is equal to 0, both for the conditional and the unconditional case, then this translates to this magnitude scheduling scheme, right, where I pick the max. This schedule estimator pair we can show is unique. They actually constitute a Nash equilibrium for a non-cooperative game that's being played by the scheduler and the estimator. So it has a number of nice properties. So then here's the picture that I promised Benham. Maybe it's not as epic as I led you all on to believe, but the red line is the mean squared error for the open loop strategy, and the blue line is the mean squared error for the observation-driven strategy. So remember with the open loop strategy, oh, and also I'm sorry, I should emphasize that I have fixed sigma 2 squared, but the x-axis has sigma 1 squared, and the y-axis is the mean squared error. So if I'm always picking the one with the largest variance, there are going to be situations when the realizations of x1 and x2 don't match the largest, the relative behavior of the variances. So what are the things that we can say? This result only depends on the even symmetry of the density, and we can extend this to any number of sensors making even vector styled observations. Okay, so it's a nice result. And as I said, to me, it was a little surprising because it was also variance independent. Okay, I can consider dependent symmetric sources. Now my conditional mean estimator is not as clean as it was before. It ends up having a kind of soft, smooth structure. In the case of equal variance Gaussians, we can compute it in closed form, and you see different versions of this estimator structure there. So you can see that we're sort of clipping things close to zero, and then being a little judicious in terms of how we scale the output depending on our received signal. We can handle arbitrarily correlated Gaussian sources in a variety of ways. So the previous result was for the 2-user case. This particular set of results is actually for a collection, can be extended to a collection of sensors of arbitrary dimension. And so what we showed before is that if I use the max scheduler and the conditional mean estimator, this collection is person by person optimal no matter what's coming in. What we suggest doing now is, if you know you have this coloration, you take your observations and you simply whiten them. And it turns out that in that situation, this overall system is also person by person optimal. Okay, again, it needs to be distinguished from being team optimal, which is the truly optimal choice. And in the 2-user case with equal variance, we can go back to that previous theorem, which gave us the soft conditional mean estimator, and take a look and see how much this whitening operation costs us in terms of performance. And so the blue line here is the soft thresholding estimator, all right? This decorrelating approach is shown here, and we see we get pretty minimal loss. And then if I just use some, the best linear estimator, I have the red curve here. So again, we're looking at the mean squared error as a function of the correlation between the two sources, x1 and x2. So that works pretty well. So to get to one of Benham's earlier questions, you know, what has to be true about these densities? What do we know? And can
now, I swear to you, this is my last question.
No, I love it that you ask questions. If you
now, yeah,
keep asking.
yeah. Now, when rho is equal to 1, right? In this case, is there something special going on when rho is equal to 1?
I mean, when rho equals to 1, then in principle, you can figure out things close to exactly, right? Because you have correlation 1.
That's right.
So that particular side information is not being exploited here.
Okay.
But, you know, but you get what you expect, right? So when rho equals 1, everybody's mean squared error is essentially 0.
That's right. That's right. Okay. All right.
Because, yeah. Okay.
But the strategy is still the same.
Yeah, I mean, in a sense,
I guess anything will work.
Yeah, anything will work.
Yeah. Okay.
Okay. So now what do we do if we have an unknown joint density, right? How are we going to solve this problem? And we are going to make a number of simplifying assumptions, but the preview here is that we're going to essentially take a machine learning type of approach and look to doing expected risk minimization, okay? So I still have this generalized nearest neighbor condition, and if I leave the estimator as is, I get an infinite dimensional optimization problem, which is challenging here. So we're going to do something that is commonly adopted, as I understand it, in the controls community and also to some extent in the communications community, which is that I'm going to approximate my estimator with a linear estimator. Now this changes things into a finite dimensional optimization, but I still have a non-convex problem, right, due to the act of the scheduling. So how are we going to solve this? So you may not have followed this, but let's look. So here on the slide at the bottom, I have the usual description of mean squared error that we're all used to seeing, all right? What I'm going to do in the next slide is rewrite this cost function as a difference of convex functions. So this mean squared error expression is exactly equivalent to the previous mean squared error expression, but now it's a difference of convex functions. This doesn't mean that it's convex, but I now, having this form, there is a toolbox that I can employ to solve this problem. So you have this difference of convex decomposition, which is shown here. So I've defined things. And there's a series of works started by this Yule and Rangarajan paper in 2003 and recent extensions by Lip and Boyd, where you can adapt what's called the convex concave procedure, which is essentially giving a heuristic to find a local minimizer of this problem. And it's like a form of gradient descent, if you will. And so you update each of these functions using the strategy shown here, whereas you update your G function, which is one of the convex functions, and then you do a minimization, go back, recompute FA, et cetera, et cetera. The little g that you see there is the subgradient of the original GA function, which is not differentiable due to the presence of those max functions. And in the case where you have completely known statistics, you can solve this problem and it works out. But of course, we started out by saying, I don't have the statistics, I have these unknown densities. And so you're essentially going to replace your expectations by their empirical means. Right, so I now have an empirically computed FA and an empirically computed GA. And so this is now reframing our problem to one where I'm doing expected risk minimization. And this empirical computation, you can think of as doing Monte Carlo sampling in order to minimize this empirical mean squared error. One of the key things that you exploit in order to make all of this work out is that our observations, in this case, are IID. And so we're going to assume that, and just again to remember that these sample functions are non-convex and also non-smooth. So you have this particular strategy. This is me repeating what I said before, where you're replacing everything by their empirical means. We get pretty good performance in practice. Now, what's interesting here is to ask the question of, can we say anything about the convergence of this strategy as I'm collecting more and more data? And it turns out, and this is something that Marcos proved just recently in the revision of this paper, which is under submission, which is that by making this mapping to the expected risk minimization formulation, we can now leverage strategies which tell us when ERM is going to work well. And it works well in practice if the uniform strong law of large numbers holds, which essentially says that my mean squared error is going to converge, essentially almost surely to zero. I shouldn't call it mean squared error, but the difference between the empirical mean squared error to the true mean squared error. And we've been able to show that if the data set is IID with a well-behaved PDF, then this uniform strong law of large numbers holds. And so the big message here is that given our framework and our strategy, even if we don't know what the densities are, we can learn what we need to learn in order to design my max scheduling conditional mean estimation strategy. And so I have some numerical results here. And so here's a kind of a Gaussian mixture problem. I'm trying to find this point here, which corresponds to my global minimum of the mean squared error. We run this iterative strategy over 100 experiments where we use 1,000 rounds of iteration, and 85% of our solutions are sort of close to the optimal cost, and 40% of them have converged to the optimal solution. It's not as strong as a statement as we would like. We would like to come up with a learning strategy that offers us better performance, but we feel like this is an important first step that tells us that these kinds of strategies can be used. And here's another example here where it's just our classical Gaussian before, but things are not IID, and we run 1,000 experiments, and the true minimum mean squared error is 1.9704. And you can see that all of these experiments are very close to that value. This is 1.97 over here, and this is 2. So we're within, 1% of the optimal solution. So again, depending on the complexity of the density, this tells us, the complexity of the density challenges how well we can learn things, as you might imagine. Okay, so remember when I started, I told you that this was the picture that I wanted to deal with, this collision channel here. And we have just spent a fair amount of time not talking about the collision channel, but talking about the design of this joint scheduling and estimation strategy. So what I want to do now is return to the collision channel, but mix it up a little bit, which is to say before, mostly because I was focusing on this 2-user case, a meaningful collision description was that if the 2 sensors communicated at the same time, then I would have a collision. I'd like to be able to treat larger networks, that's more practical, So I'm going to generalize this collision channel model to say I have some bandwidth k, which means that k out of the n sensors can communicate at any time. So now what I want to do is choose these k out of n sensors to communicate such that my overall mean squared error of estimating everybody, all n, is minimized. So again, how does it work? If I have less than or equal to k transmissions, then I receive everything. So here k is equal to 2. I've selected sensor 1 and sensor 2 to communicate. I receive their identities, 1, 2, and their measurements, and everyone else is silent. If I have 3 sensors communicating, all right, which is larger than my bandwidth constraint, then I'm going to have a collision. Okay, and this is how we're modeling the channel. So, can we design decentralized schemes, things that are entirely decentralized, where each sensor is making their own decision? What we want to do is exploit the intuition that we had from before, which says, in the 2 sensor case, this max scheduling mean estimation strategy is person by person optimal. And this suggests that if I have n observations, I want the top k of them and their associated sensors to be transmitted. Okay. So we're going to try a number of strategies. So the first one assumes that I have all of the statistical information that I need, and I'm going to conjecture that if I determine the right threshold that I'm going to assign to each sensor, that they will take their observation, compare it to this threshold, and if it is larger than the threshold, they will transmit, and if it's less than the threshold, they will keep quiet. Okay, so this has a centralized computation, but a decentralized use, right? So I know my underlying statistics, the fusion center does this computation, it hands out T to all of the end sensors, and they use that. So again, going back to things you probably learned in your first year of grad school, you can solve these problems by looking at order statistics. So I have my densities, I figure out the order statistics, and I can compute the threshold T that minimizes my overall mean squared error. Okay, so it's a little messy, but you can do it. There are a number of nice things that we can say about this strategy. First is that my mean squared error has a global optimum with respect to the choice of threshold. And in fact, this mean squared error function as a function of this common threshold is well behaved. So there are nice numerical strategies I can use to figure out what T star is. Okay, so that's good. If I compare my performance with this computed T star that everyone uses independently versus transmitting exactly the top K measurements. So this is now a normalized mean squared error versus the number, versus the bandwidth, if you will. We see that this thresholded scheme works pretty well. I'm not taking too much of a loss. Of course, with the thresholded scheme, every now and then you are underutilizing your resource because you're sending less than K measurements, and every now and then you're trying to have more than K sensors communicate, so you have a collision. So the previous strategy was nice, but it did involve knowing some side information and doing this centralized computation. Now the question is, can I really decentralize this? So I, as an individual sensor, am not necessarily going to know all of the measurements of all of my neighbors, but can we somehow self-organize, if you will, in order to figure out what the top K measurements are? Okay, and so not surprisingly, we can map this to variations of consensus. And so if you go back and think about our thresholded scheme before, this T star was a nonlinear function of my underlying statistics. In most of my simulations, I'm assuming that I have zero mean observations. So essentially it ends up being a nonlinear function of the variance in the Gaussian case. And so we know that we can learn the variance of a collection of sensors observations using a consensus strategy, and that in the limit, I will converge to the true variance. So this is us piggybacking off of existing results. So there's another way we could do this, which is to try to estimate in a distributed fashion quantiles, right? So I'd like to try to learn the CDF, the empirical CDF of my observations, and then I know where to cut things off in order to determine what my top K measurements are. Here too, we are leveraging someone else's strategy, which is this consensus-based distributed quantile estimation in sensor networks paper. But one of the new results that we have is that using the strategy, we can show that this distributed quantile scheme, its mean squared error is going to lie between two different mean squared errors. The omniscient or the genie-aided top K strategy and the genie-aided top K minus 1 strategy, all right? So I'm always going to be between those. Of course, if I know the top K exactly, I'm going to get the best mean squared error. If I know the top K minus 1 exactly, I will do well, but because I'm not using that Kth measurement, my mean squared error is going to be larger. Okay, but this is a nice result. And so how does all of this work? Okay, so let's take a look at some numerical results here. I have mean squared error versus consensus iteration, if you will. So let's walk through the different lines. This dark blue line here is this consensus strategy where I am learning the variance and computing this, T star locally. What I want you to focus on is the fact that it converges very quickly. And it converges very quickly because it's only estimating one term, this variance essentially. This dashed red line here, or fuzzy red line, corresponds to making the top K decision using this fast quantile estimator. And it achieves a much better limiting mean squared error than the consensus strategy, but it takes a long time to get there. And it's kind of hard to see because of the bumpiness of the red curve, but as predicted by our analysis, the limiting mean squared error achieved by this quantile scheme is essentially in between that of the K minus 1 case and the K case. What is this black line? This black line is essentially me balancing. I'm realizing that there's a mislabeling here, which I had not noticed before. So the black line, the black line is this quantile scheme, and the red line is a scheme that switches between consensus and quantile. And as you can see, it converges much more quickly than the black line. Okay. So I should pause for a minute here. Are there any questions? No? Okay. So another variation, which I'm just going to touch on briefly, is I can make a further extension to this problem and give my scheduler, which is going back to the original problem statement that we handled before, where I have a scheduler, I can give it a battery. And so now I have an additional cost I need to worry about, which is every transmission costs me something. So if my sensor observation is not informative enough, I should not waste energy transmitting it over the wireless network. And this battery essentially introduces coupling in time, even though each of the xi's are actually IID in time. And now we have this overall cost function, which is to minimize, essentially my mean squared error and computation cost, transmission cost against my battery. So this is how much I'm going to, ZK is how much battery I have. EK is telling me the cost I need to incur. UK is the cost I need to incur. I'm also filling up the battery at a particular rate. And then I have some limit here. So what I really want to focus on is simply what the scheduling strategy looks like, because it is very intuitive. So previously in my max scheduling case, I'm only showing one quadrant here. This 45-degree angle line would go all the way to 0. And depending on which magnitude was largest, that would tell me which one I would send. Now I sort of have the same strategy, but now there is a dead zone, right? This UK equals 0, which says don't send anything. And that makes sense because if my measurements are really small, they are not having a huge contribution to the mean squared error in terms of keeping it low. But on the other hand, it's going to cost me a transmission. The thing that's different here from the non-energy harvesting case is that these thresholds now are a function of the statistics, right? Whereas before, I had a scheduling scheme that was completely independent of the statistics. And so under certain symmetry conditions, we can actually show that our solution is in fact team optimal and not just person by person optimal. Okay, so I'm tying things up. Hopefully I haven't gone too much over time. When I started to talk about this problem framework, I suspect a number of you looked at this problem statement and said, okay, she tried to motivate it saying it relates to cyberphysical systems and IoT, but the overall framework seems incredibly idealized. This would never occur. But it turns out that we actually have done work on a real system where exactly this problem with the scheduling comes up. And so with a number of colleagues, we had a multi-year project where we were designing wireless body area sensor networks, and we instrumented grad students and inner city Los Angeles youth with a collection of sensors, and we were trying to track their physical behavior. In that situation, because of the implementation of Bluetooth on the cell phones, which we were using as fusion centers, the cell phone could only listen to one sensor at a time. And so as a result, we did have to design sensor scheduling mechanisms to determine which sensor the cell phone would listen to in order to come up with the best estimate of the behavior that the person was engaging in. And so that scheduling and remote estimating framework falls very naturally into this system, of which a prototype was built and deployed on people in Los Angeles. So as I said, this was the system that we had. Here things were a little bit different because we were trying to figure out physical state, but we had multiple sensors, we had a scheduler. We did have a wireless network because eventually the cell phone was communicating information to a server where a lot of our decisions and computations were being made. So a nice that we were able to come up with what I would say are fairly complete theoretical statements about the optimality of the structures that we should be using for scheduling. So let me tie things up. We talked about a lot of things, but there's a common theme, which was looking at the design of sensor network systems where I need to worry about communication strategies as well as estimation strategies. We have what we think of as a new idea, if you will, which is observation-driven scheduling. So the observation itself tells you what you should send, and it's a way of dealing with this asymmetric information structure. It's person by person optimal, strong improvement over this open loop approach. And we had all of these extensions, unknown joint densities, decentralized methods, and energy harvesting. Before I completely end, I want to give you another example of one of these decentralized decision-making systems that we are studying. I'm working with a number of colleagues who are microbiologists that study bacterial populations, and a particular phenomenon that two sets are interested in is something called quorum sensing. And so many strains of bacteria have the following capability. They can synthesize a molecule, they can sense the presence of this molecule in the environment, and this is where things get a little unclear, but the conventional wisdom is that if the amount of this molecule in the environment is large enough, that molecule presence is proportional to the number of bacteria in the environment. And so if the number of bacteria is large enough, then it is cost efficient, if you will, for the bacteria to engage in new collective behaviors, which occur when they express new genes. And since the expression of the gene is expensive, they don't want to activate them unless they know there's enough of them out there. So the analogy I like to use is that, and I have to be careful given our current climate, but you don't want to start a riot unless there are enough people standing behind you, okay? So these are some very new results. In fact, we're going to present them next week to our program managers, but we have modeled each of these bacterium as individual decision-making agents. We have some models for how populations grow as a function of what's going on in the environment, whether they've activated or not. This is a synthetically engineered set of results where the blue lines, the blue dots correspond to experimental data where the cells are engineered to never produce this molecule, but when it's present, they engage in certain behaviors. And then the red line or the red circles correspond to bacteria that always produce the molecule. And what happens here is that at time 4, which is about here, the molecule is introduced into the environment. And you can see that we have a really good match. We've actually discovered some new things about how to model these populations. There is a growth rate that seems to be population density dependent, which is not what we thought before. And so we're actually very excited about these results. And this comes out of a MURI that we have with colleagues all over. We are half engineers, myself, Paul Newton, who's a control theorist, and then many of you know Al Hero at Michigan, and then James Bodeker, Joe Handelsman, and Ophelia Venturelli are microbiologists, and Joe Parker at Caltech studies ants. So I think I will end things there. Thank you.
All right. Thank you so much, Dr. Mitra, for the great presentation. So I guess we can just go to questions. If you have questions, you can feel free to either put it in the Q&A section or maybe raise your hand, and I can have you ask your question as well. Okay. Ashu?
So, Ubli, if we turn this around into a design question, that I assume this has some sort of a scaling properties, and then as you add more sensors, they behave certain amount of, I guess, overall sensing throughput can be sustained. If you turn it around and ask what access mechanisms we should design, which allow a little bit more flexibility to increase that overall, I guess, sensor transmission throughput.
You ask a very good question, and I have to be honest, we have not thought about it. But I think you're right that I think, to be honest, I'm limited by the fact that, so on the estimation side, the conditional mean estimator tells you what to do, right? You don't have to think so much. There's a recipe that you follow that gives you what the optimal solution is here. And to some extent with the scheduler, we because of our goal of showing person by person optimality, we seem to be a little more limited, right? And when we think about access, it's either access or don't access, right? These are our two choices. And so one question is, do we need to rethink what access means? Like, is there some notion of partial access? And then in which case we could try to design, an optimal strategy and see what happens. I think it would get a little computationally complex, but
the other variation or other dimension in access is speed of access, which
yes.
I think is not modeled, which is
right.
This channel, either channels are good or bad, or some sensors are closer to the destination, right? The natural distances. So, if you assume that things send beacons and you kind of know how good the access is,
right?
Then should the sensors do something differently in that case?
So I will answer that by saying, in a different piece of work with a different postdoc, Niccolò Michelucci, who was at Purdue and is now joining Arizona State, we did kind of look at that question. So this was a much more networking oriented problem where what you were giving each of the sensors was a biased coin. And then based on the quality of the estimates you were making at the fusion center, you would adapt that coin, right? And so this was a belief-driven problem. And there, then, you are actually titrating resources in the sense that if your coin is close to 1 in terms of transmit, you would transmit more often. Now, the piece of that that we didn't treat there is the notion of fairness. Like, okay, you now have different access to different kinds of resources, but now are you getting enough of your information transmitted across? But the way we handled things there, again, as I said, is with this bias coin.
So I have one more question on the current slide, which is flashing.
Yeah.
How, like, based on the properties of the biological system, which of any of the assumptions in your current analysis may need to be revisited? Is it that if the population of bacterium are close by, they behave differently versus when they're separate, or?
So Joe Handelsman, who you see at the bottom, is a really prominent microbiologist. He was actually one of Obama's science advisors during his, definitely his last term, maybe his first term as well. And so she's very interested in spatial relationships. One of the things that she's been studying, and I raise this because it gets to your question of when are things different in biology and how would we use that? So I'm just going to give you the when are things different part, how we use it, I'm not sure.
Sure.
But She's studying a 3-species population that occurs in the wild. They actually grow on roots. One of these species, which is a Pseudomonas, is like the 800-pound gorilla. It exists in the largest cell density. It produces a molecule that if, and I always get these names wrong, I'm sorry, if this Johnsonite strain exists by itself with Pseudomonas would be killed. But if this third strain, Bacillus, is there, it kind of moderates the impact of this killing molecule. And so the three of them can kind of coexist together. And so one of the ways that we've thought about modeling this is as, you know, you have these cell population sizes, and there's a queue that is generating more bacteria, if you will, but the rate of generation is state dependent, but it's not dependent just on the state of the current bacteria, but also dependent on the population size of another bacteria. Mm. And so, although since you're asking questions here, let me also throw out one more thing. So one of the things that Ashu and I worked on when I was on sabbatical at Rice was looking at variations of the classical relay channel, you know, as studied by Kover and El Gamal, where you have the 3 nodes, a multi-hop link, and a direct link. And with Ophelia Venturelli, also Wisconsin, they actually have this very complex microfluidic device that allows them to separate different populations of bacteria. And they were already studying how the impact of range had in terms of the receiver population quorum sensing. So the way all of this works is that there are many things you cannot measure directly, but you measure them indirectly. And so when these bacteria express a gene or do other things, they can be engineered to basically light up. And so you measure the amount of fluorescence, and based on that, you infer how many of the bugs have activated or are producing these new molecules. And so literally just yesterday, we were talking about, you know, what would be an interesting relay problem to handle where we could maybe give some analysis. They're interested in asking the question of what's the optimal number of relays to have in this system. I think they said they could have up to 7, which it seems like a big number, but you know, it depends on what they build. And there's this weird, well, it seems weird to me, but there's this notion of signal regeneration. So I always thought of these molecules that once they bound to a site, they were sort of gone, but it turns out they can be reused. And so it may be a situation where a classical relay channel with multi-hop and a direct link is the right model for this bacterial system. So I'm actually going to show some results from our joint work, Ashu, on Tuesday to our program managers about, you know, what we were thinking about doing in terms of analyzing these systems.
Very cool. Well,
yeah, no, it is very cool. So if you want to keep working on it, let me know.
Thank you.
So I actually have just a simple clarification problem. So in the problem formulation that you had is like essentially the estimation variable were just random variables that we're estimating. Is that correct?
There are random variables that we're estimating, but you're treating them a realization at a time.
So I was wondering how the problem changes if you have indication of time, like random processes.
Yes, so that's a good question. So I actually think that well, things get more complicated. I think you end up getting MDP formulations, right? Which can be handled and are classically handled by these asymmetric information structure decision-making colleagues like Ashutosh Nair. So I think it can be done. What I'm not sure is whether it ends up being kind of a minor modification of what we did in the energy harvesting paper, because their temporal coupling was introduced by the battery, or if it's a whole layer of new complication. So, so the short answer is I don't know. The short answer and a half is that I think it's doable. What I don't know is, okay, so I'm sorry, I'm going to put on my sort of, you know, professorial advising hat, which is you look at problems and they haven't been done before, but you kind of need to assess, is this problem worth doing, right? And so what I'm not clear about is this a problem where there would just be so much computational heartache with limited intuition at the end, right? So the sort of risk payoff kind of thing. And that's what I'm not clear on. But we have talked about it. And I think actually Ashutosh Nair is working on not this problem exactly, but variants where you have correlated random processes coming in.
Yeah, just we have actually one more question from Yasaman. So she's thanking for the talk.
Okay.
Well,
She can ask her question.
Well, yeah, Yasaman, I think you should have. Yeah.
Yeah, I think I'm unmuted now.
Yes,
Can you
great.
hear me?
Go ahead.
Yes, we can.
Yes. Yes. So I was thinking about, so you talked about like a schedule that avoids collision. So I was thinking about more like in a time varying domain. So let's say our fusion center here needs to receive sensing data from like all of these nodes, or at least a sufficient number of them so that it makes a decision based on that. So then how would you envision the design of the scheduler change in this context?
Oh, when the XIs are time varying?
Yeah, so basically it's not just one slot, scheduling for one slot, but like align
I see what you're saying.
and then you basically need more than, so if it's independent, then of course, but then it's not independent.
Right. So I have a canned, I have an easy answer to that. I'm not saying it's the right answer, but what you would do, first step in that situation is convert things to virtual slots and virtual users, right? And so I can think of now all of the possible permutations that could occur. I would have these differing virtual users, right? And then they could be scheduled according to these slots in a one-shot fashion, but each slot would actually correspond to a collection of observations over time. It's conceptually straightforward. It's computationally a bit of a nightmare because there's a lot of bookkeeping that you would have to do. This is assuming that you could look at your dependencies over some finite window and, like have a block, I don't say block fading, but a block memory system.
Mm-hmm.
So that would definitely work. It's not the elegant solution, but I think essentially, the half answer that I gave Raman is kind of the half answer that I could give to you as well in terms of the next step.
Mm-hmm. Thanks.
Sure.
Okay. Perfect. I think we're right on time. So yeah, with that, thank you, Dr. Mitra, for this fantastic talk, and thank you for everyone for joining today. Again, we hope that sometime soon we could actually have you on Rice Campus in person.
Absolutely, absolutely.
But yeah, I guess we have to wait a little bit for that.
A little bit.
Right.
Thank you very much. I really enjoyed this. It was so nice to meet with everyone. And if any of the students or anyone else has questions and wants to talk offline or a separate Zoom, don't hesitate. Go Owls.
Thank you.
All
Thanks,
right.
everyone.
Bye.
Bye.
Bye.